All right, now that we have explored the idea of the Gaussian distributions, the normal distributions, the different probability functions that we can use, the posterior, the prior, the likelihood, the marginal, and also how we parameterized Gaussians using the means or the mean vectors and the standard deviations or the covariance matrices. We will now explore a more concrete example on how to create a Bayesian classifier by taking advantage of the bias rule and all these probability functions and how we could estimate those. So in this example here, this is coming from the Doing book, chapter 2. So you have access to that. Please check on the readings for that material. So here we have an example of a task where we want to sort parts like small metal pieces that could be rings, could be nuts, could be bolts, but could also be just scrap. And what we define by scrap is just pieces that we cannot really make any use of it. So the focus here is that we want to classify those. Those would obviously be worth different amounts of money. I mean, rings, nuts, and bolts, right? But if they are scrap, so you actually cannot resell those. So these would just be a waste of effort and energy and time. So depending on which part we are talking about, we would have different different prices being applied. And at the end of this chapter, we will explore more on that idea on how to essentially maximize the profit. So these are some interesting examples where, for instance, you might have one example here that looks like a boat, but is actually a scrap. You have an example that is fairly easy to distinguish. So this is a very easy example of a scrap. And then you also have an example that is actually a scrap, but it looks very similar to a nut or maybe a ring. It's actually the other way around, right? So it's scrap, but there's some features that kind of makes that specific part kind of similar to either nuts or rings. So the specific features that we are using in our data set are these two. So the first one is a six-fold rotational symmetry. So this is on a high level an idea of how symmetrical in shape the pieces are. If you have smaller values, this means that these are more symmetrical. And you have the second feature, which is called eccentricity. So the eccentricity is an idea where how homogeneous or how different from a circular shape you would have. So if you have smaller values, you would essentially have a more circular contour. We don't have to fully understand these concepts themselves, but we do need to have an idea of what the features are essentially representing, because they would be essentially defining our input space. So these would be the features that would be used as input for our model. So here we have an example of an input space because I have two features. I would have a two-dimensional input space. And here, these are very rough decision boundaries, so don't take for granted. This is just to give you an idea roughly in which regions the parts would be seated. So if you see here, the circled ones are examples of misclassifications based on these decision boundaries, because the X here would be representing the scraps, and you would expect the scrap to be in this region here. But if you have a scrap in another region, this means that this is essentially a misclassification given those decision boundaries. So the way that we would actually model our model and to some degree the decision boundaries is that we would be using Gaussian distributions for every class that we have. So we have these 4 classes. We are representing the classes as these omega values. So omega 1 to 4 are my classes. And then my classes, the posteriors would be conditioned on my inputs. So this means that I want to estimate first my likelihood, and my likelihood is represented here. That's what we are trying to model at the first place. So here we are using the nomenclature of Z to represent our input. So Z is essentially our input space or our input points or vectors, and omega are our classes. So the probability of the input conditioned on omega are the condition on the classes are essentially our likelihoods. And as I mentioned before, because you have 4 classes, you would have 1 likelihood function for each class. So you have essentially 4 different distinct likelihood functions. The way that you visually see that in this plot here is by identifying those contour plots here. So these topological curves that you see that I have previously mentioned, or these contour curves, these represents roughly the points that would be equally likely, and also gives you an idea on when the mean of that distribution would be. So you have essentially 4 of those distribution, 1 for each class that we have in our data set. So another interesting thing that we can comment is that I can relate these individual likelihoods, or I can in a way consolidate that, and that would allow me to actually find that marginal distribution that we have mentioned before. So P of Z is the probability of our input that do not depend on any class. So this essentially, you can think of it as all the individual likelihoods merged, consolidated into one single curve, and that's what you see here. And you can still see that here, because these can be thought of as a score, right? The probabilities. You can see the projection at the bottom as just our input space, which is precisely what you have in the right-hand side here. So here, that's what I mentioned in terms of the P of Z. You normally don't need to calculate P of Z, but if you would want to do that, you can do that by marginalizing the likelihood with respect to the classes. So then if you do that, then essentially you are consolidating all these curves into a single curve. So then that becomes the not conditioned probability of your input. So here you can see it's a little bit hard to see, but here is just to show the apexes that you have. So you have one here, you have one here that's kind of hard to see, and you have this one here and this one here. So you still have these 4 apexes that essentially represents the more likely points that you have for each given likelihood. So even if you have merged everything into a single curve, you can still identify those. So let's recap that this is the sort of shape that would expect from a unidimensional Gaussian. But because we have 2 dimensions, then we would actually go with the multivariate Gaussian because we want to estimate the probability distribution. We need to essentially estimate the values of our means, our mu vector, and the values of our covariances, and we will get to that in a bit. So this is just an example, same as I have shown before. And let's begin with an example where I would be actually giving you the covariance matrix and the mean vector. So if we would do that, how we would essentially calculate our normal distribution. One way that I like to do it is by separating this part here identified by the dotted red, because this part here do not depend on X. So these do not depend on your input, while this part actually does. So some authors refer to that part on the left-hand side as the Gaussian mean. So that's one name that you can refer to that. And that's essentially just that part of the equation of a Gaussian that do not depend on the input. So here we are just plugging in the values. So I have here these two terms. Because I have two dimensions, right? So then I would be getting D as 2. I calculate the determinant of my covariance matrix. After I calculate that, I take the square root. And if I plug in those values, I would encounter this value here, 0.11254. Next, we need to calculate the right-hand side of the formula. So for an input given, so imagine that we are now given a specific input, and you do need to have some input, right? Otherwise, you cannot actually reduce that to a single scalar. So then I just plug in that X and the mu and the sigma I already have, with the difference that I need to actually calculate the inverse of my covariance matrix. So I just plug in all those values, and you see that here step by step, and you see that I end up with a scalar because I have provided an input for that piece. So after I do that, I can finally calculate these the final output of my Gaussian just by using the values that we have calculated on the left-hand side and on the right-hand side. So then you would end up with the value for your normal distribution as 0.00125. That would be the probability density of your Gaussian. So just remember that this is not a raw probability because this is a continuous function. And if we would want to have actual probability, we would need to specify a range of our space and then our input space, and then that would allow us to make an actual estimate of a probability. So back to the main topic of how we estimate the probabilities. Let's begin with the prior. So the prior is that P of omega K that we have here. So this is just the bias rule that we have seen before. And before I have used, I believe I have used X, and I can recall some other symbol for X for the input and some other symbol for the classes. I think I use C, right? So one thing that I want to comment on those conventions is that we are using a lot of different textbooks and a lot of different sources of material, right? So it would be quite common to actually see the same equation expressed in different notation. And this is something that to some degree is actually intended because we want you to be able to identify what the equation is representing. So if you want to understand what an equation is representing, essentially you need to understand what each symbol with what each variable or element that is part of the equation is representing, right? So if you don't have that understanding, so definitely go back to the material and make sure that you understand every single symbol that you see or every single variable that you see in all of those equations that we present. So one assumption that we usually make, and that assumption is fairly common, is that we draw or we generate the samples in a IID fashion, meaning that they are independent and identically distributed. So this essentially just means that we are using the fairest possible way to generate or to draw those samples from our measurements of the phenomena. In this case, because we are actually using the data to arrive at some sort of estimates, right? So this is not the same as that idea that we have mentioned on the generative models. But now here, really, we are trying to find values that are good values based on the data that we saw for the function that would be the one that would actually be the generative function, the generative probability that would be able to generate those data points. So how we estimate the prior? popularity contest. So essentially, you just check the data, the proportion of samples that belong to that given class. That's how we typically make our estimate of our prior probability. That's not the only way, but that's definitely one very common way in which you can do that. And that's the way that we would be using in our examples. So next, I want to estimate now my likelihood. So the likelihood is that P of Z given omega K. So again, recall that Z is our input and omega K is our classes, our labels. So the likelihood is the probability of the input given a class. And that's what we want to estimate next. So now we are coming from a assumption that our models are modeled based on a Gaussian. And that's an assumption that we're making. If we do that, we would be able to generate, estimate the mean and the covariance matrix just based on the data that we have. So we would explore that in a little bit more detail on the problem solving. So with respect to the effect that we would see from applying the prior to the likelihood, this is what you see here is the posteriors, right? So recall that the posteriors are essentially estimated just by a product of the likelihood function and the prior. So how does the prior affect the likelihood, or the other way around, right? So that's a fair question. Because our priors in this case would be constants, so what's actually going to happen is that the overall shape of the likelihood would be maintained. But you would still obviously see some form of change, right? So the way that you would see that change happening would essentially by seeing a shift either up or down for each individual likelihood function. So each individual Gaussian would be moving either up or down with respect to that axis that lives in that three-dimensional space where you have the scoring axis as that vertical axis, and then you have the bottom as your input space. So essentially, that's the effect of applying a prior to a likelihood when the prior is a constant value, which is what we have here. And this is illustrated in that example that you see here in these two plots. So in the plot on the left-hand side, you can see based on the contour that you have one Gaussian here, and then you have another Gaussian here. If you move to the right-hand side, you see that these slightly reduced in size. And then this also was reduced because that part that could be seen here before is no longer visible. So in other words, the other probabilities or some other probability increased, which caused these two probabilities to decrease. So that's the effect that you would see. A little bit more hard to see. So if you observe these two contours here, these two decision boundaries here, sorry, you would see that there's a slight difference as well. So here you see that actually this is moving a little bit closer to these two data points. This is kind of hard to see, but this slightly increases in size. So this Gaussian that you see here, the larger one, is actually increasing in size, which explains the decrease in size of that two ones that I begin going over. So again, it all boils down to the Bayes rule, right? So the probability of my class omega k is conditioned on my input z, can be estimated by a product of my prior probability and my likelihood probabilities. So I can, as I said, ignore the marginal because we would be essentially just using these probabilities to compare one against another. So this is just showing what we have mentioned before in terms of the changes that you see. So you could see those changes as it's shown here. And these are essentially the shifts that are being done by the prior affecting the likelihood. So as I said, because the prior is a constant function, then you would essentially just see the overall shape of the likelihood being maintained. However, that overall curve, that overall surface would move either up or down depending on the relative importance of the prior. So if you have a prior that is the highest one, so then you would see essentially that surface going up. If you have a prior that is not the highest one, you would see that going down with respect to one that is higher than that one. So that concludes our example of our first classifier based on the bias rule and the modeling using Gaussians and constant priors. Next, we would explore how we can relate that model to what we call the uniform cost model, which is equivalent to that idea. One thing that I forgot to mention is that this overall approach that we have used here is called the maximum a priori, maximum a posteriori model. So this means that we are trying to maximize the a posteriori probability. The a posteriori is just the posterior probability. And obviously, we want to classify just by looking at the class that is the more likely one, the one that has the highest probability, right? So which means that you need to check each of those posterior probabilities. You have one posterior probability associated with each class. The one that gives you the highest probability would be the one that is given by your MAP, or maximum a posteriori model, which is the overall idea that we have explored here. All right, I'll see you in a bit in the next video. Take care.